Okay, so we have learned about um, several kinds of products. One, we have learned about the dot product between two vectors, which is a scalar, and it's given by UKVK in the initial notation. We have learned about W equal to U cross V, where W will be written as EIJK, UJVK, EI. This is the cross product between two vectors. We have learnt about dyadic product between two vectors, which leads to a second order tensor. So this has components Ui, Vj, which are second order tensors, and therefore the basis is the dyadic product between the base vectors. So these are the three products that we have learned. The next product that we are going to learn is called is analogous to this. It is called the scalar product or inner product between two second order tensors. So take two second order tensors A and B, and the scalar product between them are denoted by this symbol, the colon symbol, and its result is a scalar which is Aij, Bij. So here I and j both are repeated indices, so this is actually a long sum. This is actually a long sum. So uh, just like the dot product, uh, the contraction or inner product between two second order tensors A colon B is same as B colon A. Both lead to Aij, Bij. So if you have B colon A, you will have Bij, Aij, which is the same. Now, uh, let us prove now an important result about the contraction of two tensors. In fact, we will prove that the contraction of tensor A with the identity tensor is actually something called the trace of A. Let us prove that. So let us take the basic idea of uh, let's take the basic idea of the contraction and write A contraction of the identity tensor, second order identity tensor. Remember, the components of the second order identity tensor are delta ij. It's equal to Aij delta ij. Now, if you look at Aij delta ij, and remember that delta has special properties, it's equal to 1 when I is equal to j, and um, is equal to 0 when I not equal to j. If you see this big sum, you will realize that this big sum actually has 9 terms. So there are 9 terms summed together in this expression. Out of those 9 terms, because delta ij is going to be 0 most of the time, the ones that will survive are, of course, a11 delta 11 plus a22 delta 22 and a33 delta 33. Nothing else will survive. A12 delta 12 will be 0 because delta 12 is 0. So uh, this in these cases, delta 11 is 1, delta 22 is 1, and delta 33 is 1. So this will be A11 plus A22 plus A33, which is same as AMM, let's say, where M is a repeated index now. So AMM represents a sum of these three terms. So A dot I, A contraction I, not dot, A contraction of I is equal to AMM, which has a special name. It is called the trace of A. So trace of A is basically AMM, which is the sum of the terms A11, A22 and A33 especially the terms where the two indices of A are the same, some of the terms where the two indices of A are the same, and that is known as trace A. Okay, so this is an important uh, relation which says that when you multiply contract when you contract a tensor with the identity tensor, you get its trace, which is the sum of the A11, A22, A33 components of the tensor, second order tensor. The norm of a tensor is the tensor multiplied with itself. So Aij multiplied with Aij, A contracted with A gives you Aij times Aij according to this definition, and uh, raised to the power half of that gives you what is defined as the norm of A. So norm of A, just like the norm of a vector, u dot u raised to the power half was giving you the magnitude of u. Uh, Here aij raised to the power half gives you the magnitude of, in some sense it's not the magnitude, it's called the norm. It's not really the magnitude in the sense of a vector, but it's a norm, and the norm is given by this. It's always greater than 0 if a is itself not equal to 0. If a is itself not equal to 0, then this is always greater than 0. If a is 0, only then is it 0. Uh, these are some useful properties of tensor inner product. I'm not going through them. You can go through them. We use them often, but most of the time it's possible to prove them on the fly. Uh, so this is important, that it doesn't care about the order in which these two things are multiplied. This is also important for us, that if you multiply a tensor with the identity tensor, if you contract a tensor with the identity tensor, you get the trace of the tensor. So the rest are kind of obvious and can be easily proved. I'm not going through them. Please look at them, try to prove them if you want to know these kinds of quantities a little better. Uh, Let us, on the other hand, define things like transpose of a second order tensor. These are concepts that are already familiar to you, I guess. So uh, when you have a tensor A, you can define a tensor A transpose denoted by A to the power t. So this is a transpose, which is defined in this manner. So the transpose is a second order tensor which acts on U, and if you pre-multiply with V, it is same as taking the vector to act on V and pre-multiplying with U. Okay, which is the same as, since the dot product doesn't care about the order of these two vectors, AV is a vector, you can put it at the beginning, U at the end, so these two things are obviously equal. The operational definition is this, that a transpose operating on a vector and pre-multiplied with another vector V is same as the tensor itself multiplying, operating on V and being pre-multiplied with U. And also, one thing that you would note from here, and it is also possible to prove, that the transpose of a tensor is the tensor itself. So these are the operational definitions of a transpose. And now let us find the ijth component of a transpose of a vector. So uh, let us try to find the ijth component of, let's say, a transpose. So to find the ijth component, you pre-multiply by ei and post-multiply by ej. So from the definition of this, we know that uh, the transpose is defined in such a way that A transpose operating on ej pre-multiplied by ei is same as Ej coming first and A operating on Ei. Okay, so this will give you, this is A pre-multiplied by Ej and post-multiplied by Ei, so this will give you the Jith component of A. So the ijth component of A transpose is same as the jith component of A. Therefore, A transpose can be written as A ji Ei dyadic Ej. Remember, Ei dyadic Ej are the basis for all second order tensors. Any second order tensor can be expressed in this basis. Okay, so this is the first one. I don't know what is going on here. Anyway, let's go back to the notes. So, what is a transpose of a dyadic product? Again, it's easy to prove. You can prove it from what we had learned. Remember, for a dyadic product U dyadic V can be written as Ui Vj Ei dyadic Ej. So this is how we write it. It's a second order tensor. So if you write U dyadic V transpose, according to what we have proved here, it can be written as Uj Vi Ei dyadic Ej, which means that U dyadic V transpose is simply V dyadic U. So V dyadic U will have uh, components Vi Uj Vi dyadic Ej. So V dyadic U will have components, we will have these components, which is same as what we have here. So U dyadic V transpose is simply the reverse of the order of the two vectors. It's V dyadic U. Okay, so right. So now this is also easy to prove that AB transpose, A times B transpose is same as B transpose A transpose. Let's prove it. I'm doing this proving rigorously because I want you to get used to this notation. More you practice, more you get used to it. Otherwise, you get lost in the indices. So